Welcome to the basic guide on HP tuners and the PCM. We're going to go ahead and break this down a little bit, go over a lot of the tables, discuss some of the things the PCM does and some of the physics behind it and the reasoning why it does these things. Now you may be wondering why this is important. Understanding the physics and the basics behind what the PCM is doing and why it's doing it is a key fundamental in understanding actually what you're doing with a particular value. Not everything can be scanned for, so sometimes you do have to make a little bit of guesswork and back it up with data. So here are some of the more frequently used acronyms. This is not all of them, but definitely a good list to go by. If you ever had a question of what something stood for, or somebody thrown around online, this can help you out right here. This is basically the breakdown of all the acronyms in the tune, for the most part, that we'll be dealing with today for sure. So if you want to pause it here, or if you need to come back, just remember this spot in the video, and this should be helpful for you if you're still trying to learn this, if you're just beginning. Alright, so on to the fun stuff. We need to know what the PCM is actually doing. In an EFI car, the PCM is going to control the air, the fuel, and the spark. There is no distributor and there is no carburetor, so we need to tell this through the computer how to get the feeling correct. It's not the good old 2 1/4 turns on the screw anymore. This gets kind of complicated if you really think about it when we're talking about air mass and calculations. It's going to get these from several different sources, including the MAF, dynamic airflow, fuel consumption, and of course cylinder air, which is derived from dynamic air. Temperature is taken into account. There's a lot of other factors. We're not going to go through all of them, but we're definitely going to try to get our heads around that the PCM needs to know accurate information to operate properly. Alright, so you might be wondering why the PCM needs to control the air. Well, it doesn't. It actually only controls the airflow at idle. Every other case, your foot is controlling the airflow through the throttle. Now, the PCM still needs to know this calculation. It's absolutely imperative so it can get the fueling right. If it knows how much air is coming in, it can predict and spray the correct amount of fuel based on your injector data, based on your map, your RPM, and a lot of other sensors, actually, the IAT and the ECT, and there's a lot of other ones that come in. But moral of the story is the PCM needs to know the airflow, and that's what we get to change. And when we do change this, it's going to tell the PCM to add more or less fuel, depending on which way we take that. So our real fueling tables are actually our airflow tables. Okay, so let's go ahead and jump into the tune now, and we're going to take a look at those tables. When you open your tune, it's going to look just like this. You're going to have all your systems on the top, and of course we're going to be dealing with the engine today, so we're going to click on engine. Next, we want to know airflow, so we've got the airflow tab here. You see general, airflow, and then under your general tab. I should mention though, before we go on, the cylinder volume is part of the calculations, so if you have board or start your engine, you will want to go ahead and change this value to the correct value. Otherwise it's going to cause you a ton of headaches later on. Come back over to the airflow tab. We're going to look at those two tables we were talking about. You got the airflow versus frequency under the MAF calibration, which is a linear table. It's very simple and easy to understand. The hertz is basically the frequency required, or the amount of voltage being pumped into the MAF to maintain the element temperature, to keep it at a certain temperature. So it can actually tell you how much air is coming in based on the amount of electricity it needs to keep it at a certain maintain a temperature. I couldn't tell you what the temperature is, but it definitely tell you that it's pretty simple to plot this and to tune it. It's actually very easy. So we go ahead and close that out, and we're going to go over the main VE table here. You got the primary. This one I have set up as a 3-bar. We can go over how to do this later if anybody has a question on how to actually make this to tune for boost. Go ahead and hit me up in the comments or whatever, and I'll probably make a video on it later, a short one. But anyway, this table right here is going to basically dictate your dynamic airflow, especially if your MAF has failed. This is where dynamic air is going to be calculated from. So with the MAF failed, it's going to lose one of the calculations out of the fueling calcs. It's going to have to rely on the VE table. Now, if you do have a older car like a 97 or a 98, you're going to have a secondary VE table. So I'm just going to open up another tune here. You have a primary and a secondary. If you open the secondary, you'll see that you have a smaller area here If I open the primary, you can see the difference between the stock table. This is a bone stock LS1 tune. So if you see the difference here, as far as the amount of depth in the tune, many of us go ahead and tune this table on the left first, the primary. Then you're going to copy each row over to the other one just like so, and you copy the values. So like if I multiplied this row, say if I did my tune and followed the guide or whatnot, and actually had different values here, I'll go ahead and copy these to the 20 row here. And also note that when the math has failed and you are in speed density, the secondary table is your primary table. So if you fail to copy these values along as you're tuning, you will definitely have issues. It's not going to make changes. It's kind of interesting how that works, but that's just the way it is. So it's kind of annoying, but you just go along 20, 30, 40, 50, etc. As you see, just copy the same rows over. So that's your secondary VE table. Alright, so let's talk about some of the other tables so we get an understanding. Cranking VE, this is only going to be used when the engine is cranking, so it only goes up to 1160 RPM, and as soon as the engine fires up and starts to run, and this is going to be no longer in effect. We'll revert right back to the main VE in the MAF, if the MAF is enabled. Now over here on the right, we have our cylinder charge temperature. This is, to understand this table is pretty simple. Over here on the left, you have airflow on top. Over here on the left, this is your maximum ECT bias, and over on the right you have your maximum IAT bias. So this is engine coolant temp, and this is intake air temp. So basically how that works is air speeds up, it cools down, and the block has less time to heat the air up before it hits the cylinder, so it's going to bias the temperature of the actual incoming air more at higher airflows than it will at lower airflows. As the air is stagnant, kind of moving kind of slow through the block, it's going to heat up quicker from the block temp, so that's called heat soak. So this is that table is going to affect that. Now if you go ahead and click on the complex model here, this is only if you've moved the IAT sensor physically away from the intake, as in from the filter area. If you actually install it in the intake manifold behind the throttle body, that is, you can go ahead and disable this, because now your IAT is reading the exact temperature in your intake. So that actually is a pretty handy little thing right there, and I prefer. That's how mine's set up, and I like it that way. So EGR airflow over here, you have your airflow. If you don't have an EGR, then I wouldn't worry about this. If you're modding cars and you still have an EGR, then well, I don't know what to tell you, but I honestly don't know how to tune that, to be perfectly honest, because most of the time that's the first thing to go. Come back over here to idle now. So this is where most of the rest of the airflow tables are. You have your RPM. You click on the airflow tab over here and come over here to your general. And you look down here under base running airflow. You have your idle airflow. This is going to dictate the desired airflow. This is actually the value of desired airflow. So if you plot desired airflow along the ECT axis here, along column axis, you're going to get numbers just to plug straight in here. Pretty easy. You can run the Rust-K, or you just build your own table that does both gear and park neutral. It's actually pretty easy. And you plug the numbers in and you're good to go for that table until you go over to your IAC steps for set effective area. If you have to reset this and actually adjust these. I have a guide on doing that, but however, if you do adjust the numbers, you're going to have to come back to your idle airflow and redo your desired. Plug those numbers back in, and you kind of keep playing between these two tables. Every time you make an adjustment here, you have to readjust this. And also, every time you make an adjustment here, well, anywhere on here, well, basically your idle area, anytime you make a adjustment idle area, you're going to go ahead and go back to your idle, and now you have to mess with this, and which will cause you to mess with this. So you can see that idle is always a good time to tune. No one likes to do it because everything that you adjust will be affected by another thing. If you are having some other issues, like when you're driving and you're having a cruise control problem, over here you look at your throttle cracker, your rolling idle. These would be if your car just does not want to stop and you let go of the gas pedal and you're still going 25, 30 mile an hour. You might have to set these to 0 to shut down the IAC motor, as it'll close it further. So that might help you slow the car down without having to use the brakes. So as it should. Same thing with rolling idle. It's the same thing. It's another adder. It'll add more airflow based on speed, so on and so forth. All these are important tables, but they have much less of an effect than the primary tables, as we discussed. So the main VE, anytime you adjust this, it will affect every other airflow table in your idle and basically everywhere else. Map calibration, same thing. If you adjust this and you're using the map model, which means the map is active, this will also do that. So again, you have to go back, and VE is a huge one. MAF, not so much, because the PCM will always be using these two models. If they're both active, they'll use them both. If we click on dynamic, we kind of explain that. You see the high RPM disabled. This is where dynamic air is going to be disabled, then MAF is going to be the filtered result, and that's what's going to use. But we see it's if we set this number really low, it'll be 100% MAF. So if we zero that out or set it to 1, then that would be a MAF only. And then if we set that to, leave it normal, it biases. It's always going to bias the dynamic underneath this more, just like the other table, the bias table biases dynamic and or VE towards as the RPM gets farther down from this and above it, it's going to bias the MAF. But both are always in play. So if the MAF is not failed, that is, if you're running a MAF tune, then both of these are going to be used, as you see with the dynamic airflow value. So anyway, that's about it for all the airflow tables. And again, these are how we adjust the fuel. So we tell it there's more air, then there has to be more fuel. All right, next we talk about what the fuel calculations are. As the PCM knows, once we get the air mass correct, the PCM is going to use that information to spray in the correct amount of fuel. In order for it to do that, it needs to know the proper amount of fuel, basically, that the injectors can spray. So that's going to come from your injector data, or your flow rate. So that's one of the most important values in the tune. Next is going to be stoichiometry, or stoic. That is going to be something that we just set, but there can be a table value as well with the newer cars. I'll show you both of those momentarily, and as we jump into the tune here. Alright, so first thing we're going to look at is for the fueling, is going to go ahead and go over to the fueling tab. Click on that, and first thing comes up on the older, this is an older PCM, is a P01 0411. Under general, you're going to have a stoic AFR, or stoichiometry, 14.63. This is the setting for gasoline. Some of them might be 14 or 14.68. You can see that. This is basically what all the commanded values are going to be based on, and that's also how we're going to determine what our airflow values need to be based on the error from commanded. So this is a very important value. Now, if you do have a newer car or a newer tune, if you click on the same tab and you come over here to general, stoichiometry here, it's going to come up with a table. Now you see over here on the left, as this is 0.0 towards alcohol, so this is gasoline only. And then as you get over to the right, 100% alcohol is 8.97. As you see, that's changed. That's a significant change, huge difference. But that's because alcohol only needs 8.97 parts to 1 to burn, whereas gasoline needs 14.67 to burn, and or 6.3 depending on how you set that. It just has to be set up for the fuel type that you're using. So now we head back over to the older tune, and we'll check on the injector data. So if we click on the this is going to be, just leave this one alone and tell what banks what and what injector does what. If you look right underneath it, you're going to have your flow rate, and that first table here, you get your flow rate versus kPa. So as the actual intake pressure goes up, the flow rate goes up. So this would be if you have a standard setup, no fuel pressure regulator on the fuel rail. Now some will have a pressure regulator on fuel rail, like lots of trucks, and this will probably be, that's going to be a set value like this. It'll look like that. So if you have that rail pressure sensor or pressure regulator, so that's something to note. But still, this data needs to be correct. Now, this can be any number you want it to be. This is where you set this and change every other value in the tune. Basically, if you change this number, if I was to multiply this, say by, instead of the 75, I hit 7.75 and I multiply it, I just scaled the entire tune by 75%. Now I've only done the flow rate, but everything else is now going to be 25% off. I'm going to have to go and multiply everything else by the same amount, and to correct it, everything airflow related. So now you can see how this number can affect basically everything in the entire tune. So if I was going to do that, the next thing I would have to do is go to the primary VE and select the whole thing and do the same thing and multiply that by 0.75%, so on and so forth. And that would actually be a huge change, but that's how you start to scale a tune. I'm not going to get too much into that. I'm just trying to illustrate how important this number really is. So you don't want to actually mess with this outside the injector data too much. Plug in the injector data you have and go from there, and multiply and tune the rest of the car that way. The reason that you'd have to do this is the MAF has a maximum value of 512. So if you look on the bottom right corner, you'll see the hard limit. You gotta go down here, try not to hit anything else. There we go. So in the bottom left you have 512 grams a second is the hard code limit. You cannot exceed this with the older PCMs. So if you are hitting that, you're no longer getting accurate airflow estimates and would require a scaling operation starting with the flow rate. And of course the rest of these, take these straight off your injector data, plug it straight in, and you should be good to go. If you do scale it, this is where you start, and so this is kind of where the calculations have to come from, because this is also one of the things the PCM looks at to calculate air mass's actual flow rate and pulse width, and that's under the fuel consumption formula. So it's one of the 4 ways the PCM is actually determining the actual air mass. Extremely important table. So we come down here, we've got the rest of these. Again, just take that straight from your straight off your injector data. Alright, so every other table other than the ones we just mentioned is actually just an adder table. So if we look at the open loop EQ ratio, this is an adder. So anything above 1 of the value, it's going to reduce the AFR. So it'll get divided into it. It'll turn it down, you know, like if you see the example at the bottom, that's an 11.3 at 1.3. So that would be the target. So again, it only changes commanded. We'll talk about why it does this in a little bit and why this table looks like this. We'll actually come back to this one and talk about why in a little bit. As far as like power enrichment, everything else, you get your boost enrichment, you get your power enrichment, everything like that. You want to go ahead and make sure these are set up so they get built into your VE table, because it's all about commanding the fuel. All these other tables don't have anything to do with the calculations on the air mass. They're just going to change what's called commanded fuel. And since we're actually aiming for a specific target, we just move that target around. I cover all of this stuff in the other guide, the VE tuning. So if you feel comfortable getting into the tune, go ahead and watch that and show you how to do all of this stuff. Deceleration fuel cutoff, that's another adder. We get your basically, yeah, they're all adders. So if we go over to transient, this is another one. Transient fuel, this is going to be trying to adjust fuel as throttle position is changing. So if you've got a rich spike, reducing this number is going to help that out a lot. If you've got a lean spike, it's probably more, I'd lean more towards an error on your VE table. That's where I'd be looking at. Now if it is a lean spike and you did just set this down, you can move the number back up. I think the stock is like 0.4047. 0.1015 works pretty well for large injectors. You can go lower than this too. You can take it down to 0.10. Seems to work as well. Lower than that doesn't do too well, from what I'm told. Anyway, so yeah, this is a transient fuel. Again, another adder. So basically, none of this really has anything to do with the actual PCM calculations, but it has everything to do with commanded. So you want to set that up correctly if you're going to actually do the tuning to base this as your target, and or if you're under power enrichment, then that becomes the target of whatever the adder is adding at the time. You tune that with a wideband, look for the error, and you adjust. And again, we adjust the airflow to bring it up and meet. So that's pretty much how fuel works. All right, so next we're going to talk about spark. Now we've talked about air mass already, but the spark table relies on air mass to determine exactly whereabouts on the table that it actually is, because it goes by the row axis is going to be in grams per cylinder. Of course, RPM is RPM, but grams per cylinder is going to dictate how deep it goes into the spark table. This also goes back to injector data, and so if you do scale, you're going to have to move the rows accordingly by the percentage that you actually scaled. So you can't actually just multiply the table by 7.5 because that's not how that works. If we talk about it as we open up the tune here, but you have your high octane, your low octane tables, your two primaries. If you are in speed density and your math has failed, this is going to revert automatically to the low octane table. So keep that in mind if you are tuning with without the math on. Alright, so let's get into the tune and where we're looking at spark. So we click on the spark tab, we come over to advanced, and we're going to look at our high and low octane tables. Now you're probably wondering, why do we have two tables here? Well, the engine actually, the PCM actually has something called knock learning. The knock learn factor is as it increases, you're actually going to end up, the PCM will actually start to bias the low octane table. So let's imagine the value is 0.5. If it's 0.5, it's going to bias the value at one cell to the other at a 50% rate. So between those two, it'll be halfway there if they're different. Now in my case, they're not, because my high octane table matches my low octane table because I'm speed density. So I do not use the high octane table. Now if you do have a regular car and you're not trying to get too crazy and you plan on running 87 fuel, you're going to want to go ahead and utilize the low octane table as well. You're going to want to let the learning do its thing, because you'd be surprised at how much a car will knock, even stock, on 87. It's actually all over the place. So you want to let it use the low octane table. Pretty much it, how that works and why that's a thing. But if you're in speed density with a high performance engine, don't use 87. I mean, come on. I mean, like, you spend a lot of money on that engine. Don't even worry about that. So you don't have a safety net to fall back on for your speed density, pretty much. So don't be putting 87 in it in the first place. You should be okay. Now we come over to some of the other corrections we have. So right here you get your idle spark commands. This right here is going to be the table that determines the idle spark. So this one's for drive, I believe. Yeah, in drive. Yep. So this is idle. So if you, this is a nice little trick right here. You see setting these values to 30 or something high number. It'll act like a stall saver if the PCM does hit this. Now, if you notice, we're talking about cylinder air mass. You see grams. This is in grams per cylinder. So as we talk about, the cylinder air mass has to be dead on for the spark table to be useful. And if you do scale the tune, if you were to scale at 50%, say, the value at 1 would become the value at 50. If that makes sense. So that's why we. That's what I was talking about when you change injector data. That's what's going to happen. That's going to happen for every spark table that has that layout. Anyway, so you get your in drive, you get your in park, you get your overspeed, underspeed, you get your, these are adaptives. So these are gonna, this is how the PCM is gonna try to control the idle and the RPM speed. So your overspeed, you get your underspeed. They should be opposite, so they don't have to be identical. I like to put the higher values on the underspeed and a little bit lesser values on the overspeed. That way PCM doesn't pull the spark out too fast, which would set you up for an undershoot. So anyway, that's pretty much how that works. Getting to knock retard, this table here is basically how much it can the total it can pull. That's how much it's gonna. It says this is the amount of spark is retarded when knock is detected. Boom. That's how much it's gonna pull out. So if you look over here, you get your burst knock though. This table here, this is actually burst knock is actually going to be if the PCM is going to be predictive. So if you're making a quick transition, it's going to assume there's going to be some knock. So it's going to just go ahead and pull some spark on those quick transitions. Now this can really mess with your tune. So a lot of times, a lot of us just go ahead and disable this. So you just set it to a high value like 8, which is the max. And there goes that, because I don't like the PCM making assumptions and messing with my power. So that goes away. This is theoretical. This is real. So don't mess with this unless you absolutely have to, and you've gone through all the other steps to correct the spark issue, which would, number one, would be pulling spark out of your advanced tables. That's like the first thing you do to try to correct knock. So don't even try to just start adjusting your sensitivity. If you come over here and click on knock sensors, this is where you're going to go ahead and adjust the sensitivity. And based on whichever one you're using, set the numbers up, and there you go. There's the main one here, by cylinder. And if you set these higher, this thing, the knock sensors will actually be less sensitive to detection of knock. If you do have to do this, I highly recommend using race fuel, because at least that won't knock and you know it. If you're using race fuel, then you can go ahead and tune these out and tune them to a point, not all the way out, but tune them to a point where they stop registering, and check them and make sure they still work by tapping a wrench on the manifold or something, and it should register. Come over here to torque management. Last thing, look at the spark retard, look at the torque reduction. You zero out this table and it gets rid of torque reduction. That's pretty much everyone does that, so you get rid of this. But other than that, it's pretty much it for spark. And we'll go ahead and go over how that works and what the spark actually does and how it tracks here in a sec. Alright, just note a couple things real quick. If you watch this green line here, the TPS, and you're going to watch the spark advance. So it's right now it's at 24 grams a cylinder at 800 RPM, so basically sitting still. Go ahead and hit that. TPS is starting to go up, and you're going to watch the spark and how it travels across the chart. So as you see, the RPM is increasing, just easing into the throttle. It's going ahead. The air mass is also increasing, so now I'm getting the throttle a little more, kind of giving a little goose, and it jumps down towards the bottom, jumps up to 4,800, and then comes back across the top. So it travels in an elliptical pattern. That's pretty much all you need to take from this. That's anything, any table like VE or anything else, it's going to do the exact same thing. It's going to go along the RPM as it goes up. It's going to go across, and as the air mass goes up, it's going to go down. So it's going to end up on an elliptical. So as you let go of the throttle, it'll come back around, and so on and so forth. All the tables will do that have something to do with air mass and something to do with RPM, which is almost all of them. So that's just all I wanted to point out. We'll move on into the physics here in a sec. Alright, so before everyone starts jumping in and saying that, oh, that's not everything, I just want to go ahead and point out that these are the very basic physics behind everything. So the ones that we're going to look at are temperature, pressure, volume, compression, and spark. So there's a lot more to this than just those things, but for the purpose of this video, we're just going to go over those. Alright, so with temperature and pressure, those things are intrinsically linked. So when heat drives molecules apart, it basically reduces the density or the volume. However, if you trap those molecules, it's going to increase the pressure in a confined space like a bottle or something. Cold, of course, does the complete opposite and drives them together, which increases the volume. Moving air is cooler air, so as we know this, it's going to bleed off heat to other molecules quicker. More air equals more fuel, so more pressure also requires more fuel. Cold air is going to be more air, so it's going to require more fuel. Hot air equals less air, which doesn't need as much fuel, but it will get you better fuel economy. However, there is a problem here, as fuel actually has a cooling effect. So if we look at lean engine equals hot, it will produce more power. However, it'll be at the sacrifice of safety, or taking safety away. If you run it too rich, or run rich, it's going to cool it down. It'll be less power, but it'll add some safety. So basically, at the end of the day, it's too much heat with too little fuel equals big bada boom, as you see at the bottom. Alright, so let's go ahead and take a look at how that's applied in the tune. So if we go to the open loop EQ ratio under the fueling tab, go ahead and take a look at this. So as you see, with the increased volume, we can increase the fuel. So if it's really cold air, we have a huge amount of fuel getting dumped in here, and that continues all the way up until the engine's actually at operating temp. This value right here is actually a typical power enrichment setting. That's only at 104, and that's normal. And if your car has a big cam, it might actually idle right around here. So you'd be in dang near power enrichment settings just at idle, because it's cold, because we have a lot more air going in the engine, so we need more fuel to keep the AFR correct. So as it gets up to operating temp, you see it gets a lot closer to 0, or aka 1, or a normal commanded. And in some places actually it does hit 1, like right here, then goes under and a little bit over on the bottom. Now on this end, up on this side, remember, as I said, fuel has a cooling effect. this would be somewhere you don't even want to be with your engine anyway. If you're in these areas, you've got way bigger problems than just a fueling issue. But this is an attempt to cool it back down and keep the cylinder temperatures down. And at some point, the fuel does have to increase when the heat gets too much, so to keep it from getting too lean. So that is another factor. But basically, that's how it's working. So you see cold air, more fuel, hot air, and less fuel. So that's pretty much it. That's how the tune works. So the same thing goes with spark, and we'll talk about that in a sec. Okay, so now with spark, you have your advance is going to increase pressure and retard is going to decrease the pressure inside the cylinders. So keep this in mind as a general rule. More air is generally going to mean less spark, especially if you're looking at boost or nitrous or anything like that. You're always going to pull a lot of spark out. More compression, again, it's going to be less spark, because if you boost it, it's going to be more compression in there. The denser air, other than cold start, equals more dynamic compression again and less spark. You see the trend here, it's almost always going to be less spark. One note though is if you increase spark, you're going to add it's going to typically add vacuum. You can actually see that to a certain point up to MBT. At idle, that's very useful to get something to idle, right? As you increase spark, you'll see at some point the map will stop increasing. Idle spark is your idle RPM control, as we know. More spark, more power up to MBT, typically at risk of detonation from overpressure. So keep in mind, basically most of the correction is going to pull spark, now add it, and this is how you need to think as well. So don't be pushing the spark unless you really know what you're doing, and you're actually using things that you can measure it by, like a track or a dyno, which would be the two best places to do it. So other than that, tune your spark to not knock and conservative, and when you're ready to do it, make sure everything else is on point and go out there and tune it. So let's go ahead and show a few examples in the tune, and then we'll wrap all this up. Alright, this is probably the most complicated part of this, is trying to understand how spark compression and all this stuff plays together. So as we see here, we have the idle area here, and you have your wide open throttle area here. This is decel, and this area here is pretty much somewhere you can't get to, and same as this corner. But if we go back over here to the idle area, as we accelerate, the engine's going to take a big old gulp of air. As you open up the throttle body, the blade opens, air starts to rush in. As the air rushes in, the engine is going to be pushing spark, but you haven't actually got that air all the way into the cylinder yet. It's going to take a few milliseconds for that to happen, but as this travels over, dynamic airflow is increasing substantially. So as it starts to hit max cylinder fill, right about here, you're going to have to pull the spark back out because the pressure is increasing now, and so the spark actually comes back out. Because you can't just ramp this right up to wide open throttle, unfortunately. It has to be this kind of a curve, because this is where the dynamic airflow is going to be very high, and it's going to push back down, and as it equalizes with the outside, spark can be pushed back up to some degree, not all the way. You don't want to go up too high here, but the wide open throttle area right here is when you're starting to hit efficiency of the engine. So it's going to be pushing the maximum efficiency and really spooling some RPM. And spark here is pretty much a one setting, is once you hit that plateau. Sometimes it'll drop off a little bit at the end, but that's just the way it goes. You'll be at your maximum map and your maximum spark for wide open throttle right here. So this is what you set it to. You don't set it exactly the same as this because they're all different. This is all going to be cam dependent, based on your cam, your compression, and all kinds of things. That's what these actual numbers will be. And if you're boosted, you're going to definitely want to remove a lot of spark out of the wide open throttle area, because you're going to be pushing a lot of pressure into the cylinders. So usually we use the 28 rule. You take 28 as the number, you subtract the boost off it, and the remainder is your spark. So if it's 14 degrees or 14 psi, you'd run 14 degrees spark, and 15 psi would be 13, and so on and so forth. So that's pretty much how you do that. Nitrous ain't much different. A lot of nitrous builds I've seen are running down like to 10 or 12 degrees. Pretty typical, depending on how big the shot is. So yeah, you definitely want to make sure you're not pushing too much pressure, because if you do that, you're exceeding the limits of the fuel, which is the main consideration. the fuel type is basically what allows you to get more or less spark out of it. So if you do run race fuel, you can probably add a few more degrees here, right across the board almost, and you'd probably be just fine. But on pump gas, this is pretty much it's got a lot lower limit for detonation. So that's why we set the spark, and there's general rules under it. There's actually a lot more to this, but I'm just gonna go ahead and leave it at that, and pretty much say good luck on your builds, and hopefully you learned something from the video, and I hope you liked it, and I hope that did a good job in explaining the tune. And if you have any suggestions, go ahead and put them in the comments below, and or hit me up on ls1tech.com, and I'll see you out there.